There. So we already talked about sustainability last time, so I think we'll just continue talking about that for today. Still trying to get my, now it's huge. And here I complained not too long ago about other presenters not knowing the equipment. Here I am. All right, now I have a Zoom bar that's more or less. All right, so sustainability. We talked about the idea, right, that if we want to make a change, we have to come up with something that is better than what's already there. So for sustainability, that's the same way, right? We have to come up with something like, new products, new systems, new processes that are in some shape or form better than the existing ones, right? Just being sustainable does not alone make them change, right? So if I just say, well, it's sustainable, that's enough, then people are not necessarily gonna buy a different product just because it's sustainable. The good thing with sustainable, as we'll see as we kind of work through this, is that if we can make something sustainable, it usually makes it cheaper to make, right? Because we use less resources, and the resources cost money. But if we want to redesign stuff to make it sustainable, we first have to understand how we make stuff. And the traditional way of thinking about products has been using the concept of cradle to grave manufacturing, right? So we think about our product going all the way from when we get the resources all the way until we dispose of the product, right? So that would be we extract the minerals, right? That could be we're digging something out of the ground, or we're harvesting some kind of plants like for wood or something like that. We drill for oil or gas, any of those kind of things. Then we take those resources and put them into some kind of a production or manufacturing plant. We build whatever we want to build. Usually that means we need a lot of energy. And then, of course, we use it. That's kind of the reasons why we make the products. And then at some point, we will have to dispose of them because nothing lasts forever. And so if we look at that chain at an example, right, then we can look at this metal flask here, the water bottle that everybody likes. Now, this is a pretty straightforward product. There's not too many parts to it. Right? What kind of parts go into this water bottle? It's pretty straightforward water bottle.
We need the extraction of the materials that are going to be used for.
Just what are the parts that will go into this water bottle? What are the
metals?
Some kind of aluminum or something, metal, yeah.
The plastic, yeah.
There's some kind of plastic, right? There's going to be some kind of ink that we need to put the little logo here at the bottom. There might be some metal inside of the cap too, where kind of the mechanism sits, but overall it's a pretty simple product, right? It's mainly metal, and then there's some set of probably a couple different plastics that are up in the cap here. So if we think about it, right, so we'll just think about the metal for now, right? Then we have to go out and get some kind of ore somewhere, right? So this might be stainless steel, so we might get iron, or it might be aluminum, so we have to get bauxite somewhere. But something that probably looks something like this, right? So not the greatest thing to have in your neighborhood. Then once we have the material, so in this case the ore, we'll have to somehow refine it into the material that we want to have, right? In this case, it looks very much like we're using steel, right? So this is a steel foundry where we're mixing the iron ore at very high temperatures with sources for carbon so that we can get steel. And for those of you who are in industrial engineering, you'll learn a lot about in material science. You'll learn about how to make steel and what steel actually is. Once we've made all the parts and put them all together, then we have to transport them somewhere. And it actually turns out that transporting stuff all over the place is good for the economy, but it's not so great for the environment, right? If you think about there's the famous example of some kind of I think it was a yogurt that traveled halfway around the world before it gets to your plate, because like the milk gets produced in one place, and then the yogurt gets made and then gets shipped somewhere in Asia to put into packaging and then returned to us, right? So there can be a lot of transport involved these days. And then of course we're going to use our bottle for something, right? We're carrying it around and drinking from it for a while. And then we'll discard it at some point. Now, with these water bottles, the interesting thing is that we usually don't use these kind of objects until they're actually done, right? Most of the water bottles that you stop using are still perfectly fine, but they're no longer like, in the style that people want to have, so you kind of get rid of your bottle. Or maybe kind of the screw, like the cap kind of starts to wear out or something, and then the whole thing gets tossed out, when it would be more logical just to replace the cap or something, right? But nonetheless, this is kind of the overall structure that we would go through, right? So we go get our materials, we produce, we transport, we use, and then we discard, right? That's kind of our standard set of steps. Now that was pretty straightforward for the little bottle that we had there. But if you look at something else that's also doesn't look all that complicated, right, is the push pencil that we have here. But if you start taking this push pencil apart, you'll notice that it has a very large number of parts, right? There's, you kind of have the big plastic part, and then you have the rubber part here, that's a different material, and then this cone is different. There's kind of the little tip that's usually metal, then you have the clips on the back and the inside gets, so if you take all that apart, right? So if you really wanted to understand what the whole cycle of this product is, then you'd have to understand each of these parts. And kind of the structure that we use, the concept that we use to go through this, look at all this, is what's called the life cycle assessment. And so we look at every single part of what we produce, and then how it's going to be used, and all those kind of things, to see what the impacts are. And it started out solely with the impacts on the environment, but now we also think about the social impacts, right? So I think a big push in that direction has been trying to reduce or completely eliminate child labor from a lot of the products that we have, right? I think especially in the electronics industry and in the clothing industry, child labor has been a significant problem. I think right now, when we think about the social part, where we get our lithium from tends to be very much fraught with difficulties, because it comes from very limited areas in Africa, and a lot of those places are having civil wars and all that kind of stuff. So there's a lot of child labor, right? So all this kind of go in for us to look at a single product. So here are kind of the standard questions that we ask when we think about the life cycle assessment, right? So the first part, of course, is just what is the object made of, right? So for our water bottle, that was, we said, well, there's some metal, there's some plastics, and some ink. And then when we think about all these different materials, where do we get the raw materials from to make these, right? So is like, again, for our metal bottle, right? So there was some kind of metal that we used, looked like stainless steel, right? So that means we'd have to mine for iron ore somewhere. The ink was, probably some kind of chemical, so we'd have to find out what that ink was made out of. And the plastic, like, all know now after the video what plastic is made of. So what is plastic made of? Oil and gas, exactly, right? But if you want to be more general, we can say hydrocarbons, right? But that's basically oil and gas, right? So in our case, for this water bottle, right, we could say, well, I'm not sure where the ink comes from, so let's forget about the ink for a second. But our raw materials would be oil and gas, and kind of iron ore, and we probably need some coal too to make steel, right? And then where are we getting those from, right? So in our case, that we're mainly mining, and what impacts are there on the environment from us taking those raw materials and processing them into the materials that we want, right? So in the case of the metal for our bottle, right? What is the impact of taking the iron ore and processing it into steel, right? Well, that tends to come with a very high level of energy, right? Because we need to heat it up to very high temperatures. We think about the oil and gas that we need to make plastics, right? There's all kinds of side products that we create and like, off gases that we create. Those are all things to think about. And then how do those impact, the environment, people, wildlife, all those kind of things. Now, once we have our raw materials, right, we're not done. We still have to put them into a part. And so how does that impact, the energy, like the environment and everything, right? So what's the energy that we need? What are chemical processes involved in manufacturing those kind of things? All those kind of things go in. And then the next part is, of course, how is the object used, right? Is there something that do I have some kind of consumable that I have to have if I'm using that? For a water bottle, no, right? I mean, I guess you could say water is the consumable, but it's, I'm not sure that's debatable, I guess I would say. But if you think about your regular car, for instance, right? I mean, what's the consumable for your car?
Gasoline.
Gasoline, right? For most of our cars still, right? I mean, electric is coming, but the major consumable would be for a car would be gasoline, right? So if you're thinking about the life cycle assessment for a car, then you'd have to think about, well, where's the gasoline coming from that I need as I go along? For the electric car too, right? You have to think about where's the electricity coming from that I need as I'm going along. So that would be consumable. And then, of course, what happens to the object when it's no longer needed, right? How is it being disposed? Am I breaking it apart and recycling everything? Am I just, putting it into a landfill? Like, there's many different ways that it could go, right? So these are kind of the life cycle assessment questions that we ask, and on Thursday you'll kind of get the chance to kind of go through this for a project, for an object. Now, companies publish their life cycle assessments if they turn out to be useful for them. Usually they publish them when it looks good in some way or another. This one here is Ben & Jerry's ice cream. So they talk about kind of what one pint creates. So in 2013, which is older, of course, by now, I'm assuming they've reduced their footprint. 1 pint of ice cream created about 1 kilogram of CO2 emissions, which, I mean, if you think about it, that's a fair amount for just a pint of ice cream. And then they kind of break that down into their different parts, right? And you can see, of course, just the ingredients have a high impact on CO2, because most ice cream will contain some form of dairy, and dairy obviously has a big impact on climate gases because of the methane that comes out. Now, often when you see CO2 for climate change, right, then you'll see the little E at the end here, right? So it says 1,013 grams of CO2e, and that E stands for equivalent, right? Because there's many different gases that will impact climate change, and CO2 is just kind of the first one that we started talking about. But things like methane, which are like, there's a lot of methane coming off of dairy, that also has an impact, actually has a stronger impact than CO2, that's kind of represented by that equivalent, right? So I don't know, a square, a cubic meter of methane has like, X amount equivalent to CO2. So that's how that goes. And then the next biggest chunk is transportation, right? So that's, I think those are things that we really have to think about when we buy our ice cream. Especially if you think about it, if we're in Costa Rica and we're buying Ben and Jerry's ice cream, right? I mean, I'm relatively certain that there's no production facility in Central America anywhere, right? So that's being shipped all the way from the US. So that's a fair amount of CO2, and it's going to be on ships most likely. So there's going to be a lot of CO2 emissions, right? But you can go through, and now you can think about all these kind of things. They also talk about other things that other than just CO2, right? So they say how much electricity they use, but this is now not broken down per pint. This is now just in general, but you could divide everything by 136 million, I guess. And then another big chunk, of course, is water. They use a lot of water, and they produce a lot of solid waste. Now, if I would know what 160 million pints, how much a pint weighs, I guess we could start converting to how much that's relative to the product. But I guess that I should have done that beforehand, right? But this is kind of a life cycle study that they've done. Now we don't see it broken down into this part, this part, this part, but this is kind of in general. And here, really focusing on a single output, and that's carbon dioxide. So that'd be one. Here's one that you're now familiar with because you watched the video, right? So this is the life cycle of a plastic bottle, right? So we use oil, or in many cases it's natural gas, basically just to make our little bottle. It's, again, if you do material science, you'll learn all about the details here. We're not going to go through it, but it takes a lot of energy, aside from just the oil that goes in to produce these, because again, a lot of these processes happen at high temperatures. We'll see that that's something that comes up again and again. And so once we've produced all our bottles, then we have to bring them somewhere, right? And we have to make sure that they're in the stores and all that kind of stuff. And then afterwards, we toss them out. And I mean, this is older data, but I'm relatively certain that number hasn't changed significantly, right? So the majority of those plastic bottles get thrown out. If you just walk down the street, there's little plastic bottles everywhere. So it's unfortunate. Now, the parts that we do collect usually do not get recycled. Most of those plastic bottles are going to go into a landfill where they're going to stay basically forever. I mean, they're going to break down eventually, but it takes a fair amount of time. Some of the bottles that we can create are actually very, very easy to recycle. So we could potentially make new bottles out of them. Now, most of the times we actually don't recycle. We usually downcycle, especially with plastics. And so, like, something that makes a nice clear plastic bottle for drinking may or may not be able to reuse to make a new plastic bottle for drinking. It might be recycled, or might be reused as a plastic that's of a little less quality. So it's not really a fully closed loop. Now, the thing that is surprising to me is that, I mean, obviously drinking water out of those little bottles is not only a great waste in plastic, but it's also surprisingly expensive, right? I mean, if you go to the store and buy a little bottle of water and compare that to how much you pay if you get the water out of the tab, then that's really quite amazing, the cost difference. And in many places, the water that you get in the fancy little bottle is the same bottle that comes out of your tab. Unless it's kind of very specifically on the label. In the US, there's multiple different kind of levels of what you can call your water. But like, if you think about Aquafina or something like that, that's just filtered tap water, right? That's not special spring water or something. So it's always kind of interesting to me. I've been droning on for a while here. Any questions? Everything good?
Yeah.
Everybody who has a little water bottle kind of slowly moved it behind them so I can't see it. So nobody has to feel bad. No. All right. What else? So now we've seen what our products can do. So how do we make them better? Right? Obviously, us as engineers, we always want to make our products better. And if we want to think about sustainability, then how can we make something that's more sustainable? I still think that we'll never get to the point where we can create something that is 100% sustainable, because there's always losses, but we can at least get very close to it. And of course, we're in a class that is called bio-inspired design. So what we'll do is we'll look to nature, and we'll go through kind of each of the steps that I said before, right? In the concept of cradle to grave, and we'll talk about each of those, how we do it and how nature does it. So let's start with extracting minerals, right? Extracting minerals, obviously, we dig them out of the ground, right? That's what minerals are. They're things that are stuck in the ground somewhere. This is one of those where it's relatively close to the surface. So we just scrape it off the landscape. This is not something that's very pleasant to look at when you're around, right? That leaves behind something that is completely desolate, looks like a moonscape, right? If you kind of look in here, you can see kind of this would be kind of the height of a person, right? So it's a very big piece of machinery that's grabbing material off the side, and then it has like a conveyor belt up here to bring the material out to sorting and processing. So this is basically what this looks like, or what it could look like. These places look quite devastating. Now this is not an actual picture. Does anybody know where this is from? Now it's a little bit older. First put it in, it was new, but any Star Wars fans here?
Yeah, between.
It's Andor. It's the planet where Andor grows up. So that's, you can tell I'm a Star Wars person, right? But it looks like, this is a fictional depiction of it, but it's not that different. Right, I show you the picture of the big open pit mine before, right? So these places are really, they're really devastated once they're done, right? So this would be an actual case, right? You can see that obviously nature is not going to just come back after this, right? So it takes a lot of effort to get these places to come back. Here's another picture, right? So these can be a very big problem, and in the US, there's a lot of talk about the concept of what is mountaintop mining. So if you have materials that are relatively shallow in a mountaintop, then instead of drilling down and finding the places where you want to work on, you just remove the top of the mountain, right? That's basically what's happening here. And of course, that is devastating, right? You can see over here, for instance, that's one of the places where they're taking all the stuff and just dumping it. And of course, whatever little valley was there is no longer in existence, right? So that can be difficult for the environment. Now, how does nature do it? Well, where does nature get its materials from? Well, it gets its materials basically from the atmosphere, right? You can kind of see here, if you think about a tree, right, then most of the mass of a tree is the wood, right? And the wood is basically made out of CO2, right? So it's all carbon based. So the materials that the tree needs to grow, it takes directly from the atmosphere. Then the next biggest chunk is hydrogen, which also gets from the atmosphere, and then only, what is it, 1% or something like that. I guess it should be, yeah, 1%. All that's the only part that's kind of what it takes from the ground. Now, in our case, we do it the other way around, right? Like pretty much everything that we use to construct something, we're taking out of the ground, or if it's trees, we cut them down. But it's the same idea. Now we can start thinking about doing a similar thing, right? So people have started thinking about what can we do if we get to the point where we can actually pull enough carbon out of the atmosphere to combat climate change, then are there things that we could do with that carbon? There's a person on the top there holding up a bag that is made out of carbon that they pulled out of the atmosphere, right? So it's basically just using it for something. We're creating more and more kind of parts that are based on carbon fibers. Carbon fibers have the advantage of being very strong. They're not quite as shatter resistant as we would like them, but they're still very strong. And they're relatively light, right? So they're stronger than aluminum and lighter than aluminum. So we can use them, and we like to use them especially in places where weight is important, right? So like a sports car, obviously you want to have the sports car as light as possible so that you can get a higher acceleration, because force is equal to mass times acceleration, right? So if you have a limited amount of force that you can use to accelerate, then if you reduce the mass, you accelerate faster. Of course, another place where weight is very important is in the aerospace industry, right? So any plane that goes up, if I can save a couple tons of weight off of my plane, then I can fly farther or use less fuel or whatever. Another big thing that's coming is what are called carbon nanotubes. Those are basically a ring or like a sheet of graphene that's folded on itself. And turns out that graphene, which is kind of just a single layer of carbon atoms, has very interesting physical properties. So it's an excellent conductor for electricity and for many other things. So it's a very, very cool product. At the moment, creating these graphene sheets, though, is very expensive. So it's not quite yet ready to be used. And then the last thing that I have on this list here, what we can get from the atmosphere, we can actually create a synthetic methanol out of CO2. Right? There's a chemical process where we can take CO2 and basically add some more hydrogen to it, and we go from CO2 to a synthetic form of methanol, which we could then use to power our cars. Right? So we could find a sustainable version of gasoline if we used CO2. So that's pretty exciting. But again, those are small things that will explode. So that was our mineral extraction. How about production? Well, here are some pictures of places where we're producing stuff. And I think if you look at these, one thing that is that goes into each of these is there's a lot of energy involved, right? So on the top left here, we have, does anybody know what this is? I guess I should put it the other way around, get you guys awake a little bit. What's this up here?
Another refinery?
Some kind of chemical refinery, exactly, right? So this is somewhere where we're taking something, and these large towers that you can see everywhere, right? Those are usually places where we're breaking stuff down, and they kind of condensate at different levels and all that kind of stuff, right? So these are it's a big chemical plant. A lot of electricity goes in there, and a lot of other things for heat, right? So might be natural gas or something. Over here, we have, again, a place where we're creating steel, right? You can see how hot it is, right? So it's basically we've melted the iron ore down and to the point where we can pour it out. So obviously, very high heat. We have a factory down here where we're welding car parts together to create cars. Obviously, running all these robots takes a large amount of electricity. And if we want to create electricity, then we're having some kind of electrical power plant here. Now, what kind of electrical power plant is this?
I think that's like a nuclear power plant, maybe,
Or a coal?
Why would you say nuclear?
because of the flood with smoke coming in.
Because the towers? You know what I'm
Yeah,
saying?
if it's nuclear, it shouldn't be fumes.
So like these towers are cooling towers, and yes, people associate them with nuclear power, but they're actually any kind of anytime I'm heating something up, water up to run a turbine, I need a cooling tower. So if this were a nuclear power plant, then this building back down here would have a little dome-shaped area where the actual reactor sits, right? It's always kind of a little egg-shaped thing. But I heard somebody else say coal. Why do you think it's coal?
Because it's the other most common power plant, I guess.
Not anymore. At least in the US, natural gas is overtaking coal because natural gas with the oil, with the shale fracking is cheap. No, this is definitely coal. You can see this is where the coal is coming in. And you can see how dirty coal is by just looking at the side of this building. I hadn't noticed this before. But this is where the crushed coal is being pulled into the building to be like, you know, so the boilers are somewhere in this building. And you can see this whole side of the building is black with coal dust. Right, so this is a coal-fired power plant, which of course there are none in Costa Rica, which is great. Right, but what all these have together is that whenever we want to produce something, as humans, we use a lot of energy, right? Usually a combination of energy, and that shows itself in heat, and it shows itself in pressure. How about the environment, like the nature, right? So in nature, everything that's being created, right? Again, if you think about this tree growing, right, that's mass being created, right, is not happening at a very high temperature or at a very high pressure, right? And there's no pollution coming off when I'm creating this, right? I'm not burning coal or something to create a plant. There is a waste product that's coming off of my tree, but what's the waste product that's coming off the tree?
Oxygen.
Oxygen, right? Which is great for us. It's not, it's a waste for the tree, but obviously it's like, you know, essential for us because we breathe oxygen, right? Our bodies require oxygen to work, right? So that's kind of another one of those where nature produces a waste on the one hand, but that waste is being used by somebody else as a source, right? So there's a loop there. Another thing that we talked about before is that in nature, there's kind of the idea of being benign by design, right? So there's benign just means like not threatening, right? And so there's nothing that nature creates, it can't also break down, right? It might be dangerous to, like, you know, that little stinger there has something on it, which looks like some kind of it's going to be a poison or something, right? So obviously it's bad for whoever gets stung, but it's not something that will persist in nature, right? It's not like some of the things that we produce that are not going to break down ever, or at least not in reasonable amounts of time, right? If it takes longer than my lifetime, then that's kind of never. And of course, we can do similar things, right? So we can, instead of right now, our production means are probably not going to change, right? We can't make plastic at room temperature, or at least not very easily. But we can at least think about where we get our energy from, right? And so here are 4 ways that we can get energy that have a lower impact on the environment, right? So we have some solar panels here that we're getting electricity. This is the wind farm that's sitting right above Santana. This is one of the many hydro dams that we have. Now, this is the hydro dam as it's at its most spectacular, right? So there must be very high water because they're like, you know, these are kind of the overflow gates and they're open, going full steam. Usually you would not have the water pouring across here because you want to use all the water in the turbines that are sitting down there or something, right? So that's when you see, in usual operation, you see water kind of coming out very fast at the bottom. But this is close, like, you know, the dam is basically close to, or the reservoir is very close to being full. And if you have a dam and you're operating the dam, the very, very last thing that you ever want to have happen is to have water go over the dam, right? So these are design gates for the water to flow through. But if the water ever gets to the point where it goes over the dam, then it is time for everybody to start running really fast uphill. Because that dam is going to fail within a very short amount of time, right? Dams are really bad at having water going over the top. That's why they have the emergency exits here. And this is probably a little long ago for you, but there was a couple of years ago, there was a major disaster in California because they were trying to let the water go over kind of their emergency overflow, but that overflow failed, and so the water started going over the dam and created a catastrophe, right? So that happens. And then the last one down here, what do we have? What type of electricity production do we have at the bottom here? Somebody mentioned this like a couple weeks ago when we talked about energy, I think.
Geothermal, maybe?
Geothermal, exactly, right? So the idea of geothermal is that you drill a hole into the ground, you find rocks that are nice and hot, and then either there's sufficient amount of water down there and you basically just bring that water up and run a turbine, or more usual is that you pump some water down in kind of one spot, it goes through the hot rock, and then you pull it up somewhere else when it's very hot, and then you run your turbine. Now these types of that kind of power has very little impact on the environment. Obviously, you have to drill some holes, and you'll have power cables run around, and you have it looking like there's something crazy happening because you get all this steam coming out, but it is really just steam, right? It's not CO2 or some other kind of byproduct of something that you're burning. It's just clean water steam. Some of these smell a little bad because the water that you get up has maybe too much sulfur in it, but usually then you would try to kind of knock that sulfur out before you allow it to go out the smokestack. Now for hydropower, the impacts are a little more extreme. Of course, once the the hydropower dam is in place and everything, it's great. There's very little impacts on the environment. But in most cases, just like the one here, right? So you closed off a valley somewhere and then flooded everything that's behind the dam, right? And so that can have obviously very big impacts on the environment, but also on people, right? So people like to live in valleys, and if you flood them, then you can't live there anymore, obviously. And there's always very interesting stories about the little towns that get flooded, right? And I think it might have been Argentina, but I mean, like all of South and Central America is kind of in a drought situation, even if we don't notice that in Costa Rica quite so much. But there's a lot of places where these large reservoirs are starting to run really, really, really low, and so you're getting these old villages basically reappearing out of depth, and it's very spooky to be around them. So that's the different types of power that we could use to run our systems. Now the good thing in Costa Rica is that we have access to all four of these at abundance. The one that's kind of done, I think, is hydropower, just because there's really not an interest in building new hydropower plants in the country. But I think solar and wind certainly have a lot of capacity that can still be tapped into it. Hydrothermal as well. So that would be when we create our stuff and we produce our stuff, right? So all the energy we need for production. Let's think about disposal. So litter is everywhere, right? So this would be the bottom of a forest. You can see this must be a pine forest, right? You can see all the pine needles and mixed in with some other leaves. Of course, now back here in DC, we're just getting to the point where the leaves are starting to fall. But even in Costa Rica, where we don't have kind of the standard fall cycle where leaves drop, right? You still get a lot of stuff on the ground in the forest, right? There's just old leaves, old branches, all that kind of stuff. And we as people do the same thing, right? We throw our stuff everywhere. Unfortunately, the stuff that we throw out are plastics and they don't go away, whereas leaves, go on the ground and then they get decomposed and they become fertilizer for the next set of plants, right? So we have to think about how can we design stuff that we don't just throw in the ocean in this case. A lot of interesting stuff in there. Right? So if we throw something out in nature and it's a natural product, then life goes on, right? That's just stuff slowly but surely will decompose, right? Even if it takes a long amount of time. This is an apple slowly going bad, right? So it takes a couple months for the apple to actually be completely gone. Which is great if you have a bunch of apples, you can store them for a long amount of time. I remember where I grew up in Germany, that's kind of apple country, and so we would have, apples way out into spring that we would have, stored from last fall. And then, you can see like stuff slowly decomposes, right? We can still see basically where the leaf originally was, right? We can see the main stem of the leaf and then the main veins going off of the leaf where it slowly but surely got eaten up. And then, after that stuff will grow again. And, the cycle continues. And again, the idea is that in nature, right, that we have this cycle of nutrients that never breaks down, right? So we have the little whatever this is eating the plant here, and then this, I guess, worm or larvae or something gets eaten by a bird, and the bird gets eaten by the predator, and then the predator dies, and the microorganisms come and break it down, and then there's new nutrients for the plants to go, right? So there's a nice cycle that's going on and on and on and on. And kind of the little video that looks a little bit like a gummy bear over here, the red one. That is basically the idea that nature has an enzyme for anything, any molecule that is produced, and that enzyme is there to break down whatever it is, right? You can see, like, in this case it's making stuff, but this orange one here, it's breaking stuff apart, right? And so the idea is that there's nothing in nature that can't be biodegraded, right? Everything falls apart. And again, we came along and designed all these polymers that really don't break down readily, and that we don't necessarily even have things that we can use, like, artificially to break them down. So based on all these kind of things, we can come up with kind of a set of things that we should think about when we want to design something that's sustainable, right? And so it's called, because it's a nice rhyme, it says 5 to thrive, right? So 5 kind of concepts that we want to take on. First one is that we should use materials without mining, right? Again, nature takes most of its building blocks for biomass out of the atmosphere. So we should come up with things to do something similar. There's power without pollution, right? So again, most of the energy within nature comes from photosynthesis. And so we should try and find something similar. The concept of benign by design is that everything that's in nature can be broken down by nature, right? So anything that we would want to produce should be easily broken down within nature. And then last two, I guess we didn't talk about as much, or at least the fourth one, which is ingeniously effective, right? Is that basically everything that is in nature uses its resources to it, like, with the highest efficiency. There's very little waste in what nature does. And then the fifth one is that everything is within like a cycling loop, right? There's nothing that is lost. And again, we usually, when we do what we talk about recycling, we usually talk about downcycling, right? Taking something, back, like, for instance, glass bottles, right? So if you have a nice clear glass that you want to recycle, then usually you can't make a similar quality of glass out of it, because there's, as you're recycling it, there's all kinds of other glass that got mixed in. All right, let's talk about some examples where we can think about, or where we're starting to get solutions for the recycling part, at least. So one big issue that we're running into, and that issue is not going away, it's getting worse and worse and worse, is electronic waste, right? So we have electronics to the nth degree. I'm sure, well, I'm sure, I know that everybody here is looking at electronics right now. Some of you, like me, are probably looking at multiple different electronics at the same time, right? I have my laptop over my big screen, my phone is right next to me. And that's just the stuff that's sitting right in front of me, right? The rest of the house is full of electronics as well. And as electronics go, right, we're developing them faster and faster and faster. So we tend to throw out electronics regularly. Because we get something that's faster, that's better. Right. So like every couple of years we get a new cell phone, and our phone may or may not be working at the time, but the next big thing is out and we want to be part of using the next cool feature, right? Or the laptop, something goes wrong in your laptop and the laptop goes, like you don't try and fix a little detail of it, right? Because might as well get a more powerful laptop. Now the problem with that is, of course, that all of those electronics wind up maybe not necessarily with these two guys, but like going to waste. Electronics are very difficult to recycle because mainly because the way that we construct them. We construct them to stay together. We don't want them to be falling apart, right? Think about your phone. You don't want the pieces of your phone to be falling off all the time because then your phone doesn't work. So they're designed to be stuck together. So once they're done, it's really hard to kind of disaggregate them into their separate pieces. And just grinding them up and then trying to extract different minerals is also not really very doable. So at the moment, we're really kind of at a point where we're creating too much waste. And that's one of those things where kind of when we think about life cycle assessment, where both the social and the environmental part come in, because a lot of those electronic waste that we have doesn't stay in the developed countries, but gets basically discarded into developing countries, where people are, these two gentlemen here, working at in conditions that are probably not quite optimal, right? I mean, they're not wearing any kind of protective gear, and once you start to really break stuff down, then there's on a lot of the chips, there's a lot of lead. At least traditionally, that's changed over the last decade, but there's a lot of environmental impacts that are not so good. So what can we do? Well, we can start thinking about changing how we design stuff. So there's a group that's developed this new substrate for a chip, right? So this is not silicon based, but it's a different chip, and they're basically printing whatever they need onto that little kind of transparent material. And the cool thing about that material is that it's dissolvable, right? So if you stick it into into this case it's water, but I'm sure they have ones that are not water soluble, because that obviously can be a little difficult. But basically what it does is it dissolves away kind of the background, kind of where everything is stuck onto, and then you have these little wires and whatever's on there, and then you can easily recycle those, right? So you get away from the issue of having to kind of melt the metal off of the silicone, which obviously takes a lot of energy, right? So that's a very cool step, and industry is starting to think about how can we use this. Now the real problem is that silicone is just really good at what it does, and as kind of the main component of a computer chip, it's really hard to compete with. And it's one of those things, right? Just like the Buckminster Fuller thing, right? So we have to design something that's not just cool for the environment, but it would have to beat silicone at its own game to really get there. But we need to make steps, right? Nothing is going to happen in one big jump. Another big waste that we have to deal with is packaging. So we already were sending around a lot of packages, but of course with the pandemic, stuff being delivered really kind of got out of hand. Now Costa Rica is not quite so bad because we don't have direct access to Amazon, but otherwise we do the same thing, right? I mean, here in DC, it's just as fast and easy to order something on Amazon than to go to the store and get it. Right. So there's a lot of packages going around. And of course, with those packages come a lot of packaging material, right? So here's just a huge amount of packaging material spilling out. And so we have to think about how can we continue without creating all this packaging, right? Because maybe if you just go back for a second, is like, a lot of this is kind of styrofoam type packaging, and that's really bad for the environment, right? Because styrofoam is one of those things that we cannot recycle one little bit. All we can do with styrofoam is burn it, basically, to get rid of it. And that releases all kinds of fumes that are toxic. And of course, just making styrofoam is it's very cheap, but it still takes a lot of energy to create. So it's not a great product to use. So people are thinking, well, what else can we do? And so people have come up with the ideas that instead of manufacturing styrofoam, let's come up with ways to create our packaging that we can grow it. And so all that you see here is basically the part of the mushroom that we don't talk about very much, right? So it's called the mycelium of the kind of the little roots, I guess you can say, but they're more than that. And so we can take those and we can mix them together with some substrate, and then we can basically grow ourselves the material, that kind of the packaging material that we want to use. And so that can be very, useful, because we can, first of all, we can create any shape that we want to, as long as we can make a mold. And secondly, it does not take a huge amount of energy, right? These fungi grow by themselves. You just have to get them the right substrate and moisture and all that kind of stuff, and then you let them grow. Like, you kind of have a little video here where it's kind of growing into there. And then you can get all those shapes, right? So it's very little energy. We don't have to go to high temperatures or high pressures, and we can get this material. And there was actually, not last time, but the one before, 2 years ago, when I taught this class, one of the groups that was did this for their final project, and they actually went so far as to try and grow some packaging material. Now it didn't work, because I don't think they had the right type of mushroom to grow the material. But I thought it was pretty cool that they at least got pretty far along the process. It had some cohesion, but it wasn't necessarily very strong, right? But this would be something that could replace styrofoam. And another thing that I don't think I have one here, but one thing that's really become big in packaging over the last decade is using cardboard in more inventive material and more inventive ways, right? So it used to be cardboard was like a box, and then whatever you put in. But now cardboard is used in all kinds of ways, and the thing that you see very often are kind of these cardboard kind of brick-like structures that are basically like a piece of cardboard on the top and a piece of cardboard on the bottom, and then you have kind of a honeycomb of thinner paper in between. And so the great thing is that it's relatively light. It can be very strong, right? So you can have like pads this big that I can stand on, and they don't crush. But they're easy to manufacture. They're easy to cut, so you can make them into any kind of shape that you want to. And of course, it's paper, right? So in the end, we can recycle it to create more paper. And worst case scenario, you'll have to cut down another tree to make more paper, but we can always plant more trees, right? So there's many things that we can think about when it comes to packaging that is not styrofoam. It's just styrofoam was very cheap, and we didn't think about the environmental impacts very much. All right, let's step away from this a little bit and talk a little bit more about the concept of recycling, and basically how do we try and move away from the concept of cradle to grave and come up with something that's more sustainable, right? So I'm going to show you this basic picture a couple different times for a couple different situations, and so this kind of goes through time, right? So if we say we have a limited number of resources, right? So we're on a finite planet, right? So nothing that we have will last forever. And if I take those resources and I build some products, right, then eventually I'll get some waste. Now, if I keep on doing that, then of course my resources are going to go smaller and smaller over time, and my waste is going to increase. And at some point, we're going to run out of resources, right? I mean, that's just the way it goes. Of course, when we started the Industrial Revolution, we kind of thought that most resources were limitless. We just had to find them, right? So especially with coal and things. And then when we went to oil, at some point we found out that resource is not limitless. Now, in the late 80s, early 90s, the concept of peak oil was around, where people thought we kind of hit the maximum amount of oil that we're ever going to find. But of course, then we started fracking, and that released a whole bunch more. So it's limited, but it's not running out tomorrow, I guess. But nonetheless, sooner or later, it's going to run out. And of course, we're producing more waste. So then we can say, well, let's improve on this and let's recycle. Right. So again, we have our limited resource, we start building products, and we create some waste. Now, some of that waste, the light green one, we're going to say like, well, you know what? We're going to recycle. So we're basically adding it to the resources that we have. Right. Which means that, of course, we're using less of the resources that are out there because we're replenishing the resources that we have. You could say it the other way, right? If we think about if this were, I don't know, you know, plastic or something, right? So we have our amount of oil that we have is limited, right? And so we produce some plastic, some we throw away, and this other one we put back and basically replace oil in the cycle. So we can make more products. We can create more. We'll create more waste, but we're not going to create as much waste because, of course, some of it is going to be recycled. Keep on recycling, and that keeps on going on, which of course means we're going to use less of our resource, right? If you think about the last one, we'll run out quickly here. Kind of takes us a lot longer to run out, but as you can see from the picture, right, we're still getting some level of waste. So at some point or another, we are still going to run out, right? It's not going to be a complete savior. And that's where the new concept comes in, and that is what is called cradle to cradle, right? Before we said cradle to grave, we produce, we use, and then we dispose, and that's it. Cradle to cradle means that we take our resources, we produce, and then once we're done with using it, then we basically break down the product that we have, and reuse everything that's in there. And so that means that's the input for the next product, right? So, and we think about two different kind of loops that we think about. We think about the biosphere, so everything that's biological, and then the technosphere, everything that is technology that we've built up. And so the biosphere, it's all about decomposition, and in the technosphere, it's all about recycling. Right. So if we had a completely closed loop, then we would not have to go out and mine new lithium for our batteries, right? We would have enough waste lithium from other things that we would be able to just use that to create our new parts. Now, the issue, of course, especially with the example of lithium in batteries, are that we're using more and more batteries, so we're using more and more lithium, so that might not quite work. But this is the general idea of cradle to cradle, and if we think about that in our little kind of cartoon here, right, then basically we'll have really no waste at all, because all that the product, once it's done, gets recycled back and kept on using it. That means that our resources will be limitless, right? Because we're not taking a whole lot of resources out. And of course, from sustainability standpoint, right, if we go back to what we talked at the beginning, then that is the perfect process, right? Because we're not taking out any more resources, so it will be sustainable. We could do this for generations and generations without having to worry that that our coming generations are missing out on something because we used up all the resources. So when we talk about cradle to cradle, there's three principles, right? The first one is that waste is food. Everything that's a waste on one side is a nutrient for something else. We need to use renewable energy to run this, because obviously if we're burning coal or we're burning we're burning gas, then at some point those resources are going to run out. We're not making new coal or new gas at the time that at the same rate that we're using it, right? So it has to be something something renewable. And then the third principle is that we want to have as much diversity as possible, right? Because if we only have one thing, then if one thing fails, then the whole thing fails, right? So we want to have diverse solutions to everything, so that if one system is in trouble, then the other systems can kind of take up the slack, right? So again, we think about if we think about climate change and we think about renewable energies, right? There's never a, well, let's only use solar power or let's only use wind, right? No, it's always let's take all the different options that we have and use them next to each other. So if there's a problem with one, it doesn't we're not doomed from it. And so again, we can think about these in these two cycles, right? So if we say it's always difficult in the cycle to start, but if we say, for instance, we're starting right here, right? So we want to create a t-shirt, so we're getting probably cotton and out of the environment. We're producing our t-shirt, we're using solar power and we're using wind power to do this, right? So it's nice sustainable. Then we have our t-shirt, we're going to use the t-shirt for a while. And because the materials that we built in are all natural fibers, like once we're done using it, we can use decomposition to kind of have it fall apart. Once it's all decomposed, it's basically a whole bunch of nutrients that then create the new plants and so on and so on. So this will be a closed loop. And again, this is kind of the ideal version of it. There's obviously going to be some level of loss, but much better than what we have now. On the kind of technical side, right? So we have some kind of raw materials that we use to produce. In this case, it looks maybe like a TV or a computer, and we use it for a while, and then instead of throwing it out, we basically give it back to the manufacturer, and the manufacturer then disassembles it, and all the pieces that come out can be reused to produce something new. Right? So ideally, it would be kind of components that we can reuse, right? Like separate capacitors or whatever. But if necessary, it can be broken down to kind of raw materials, and those raw materials can be remade into the thing. But the real big step in here is the take back, right? And so that's something that factories and manufacturers are starting to do because they're required to. So there's, if you think about, for instance, a lot of the your used phones, when you trade them in for a new phone, if they're still good, obviously they'll resell them to on the used market. But if they're kind of really older, then they will take them in, and that gives them like a credit with whoever's overseeing all this kind of stuff. But the idea would be that in the future that everything that you buy, you basically you hold on to for a while, and then it gets returned to whatever company that created it, so that they can pull it apart. And the reason why this is a very important step is because that then will make the companies and the designers create their products in a way that they can actually be taken apart, right? Again, right now we're building things that we can't really take apart. And another thing here is that when we think about how we like the whole cycle of the recycling, is that we start out with something that we traditionally produce that will have some kind of level of negative impact, right? And then we'll start to increase the positive impact of it at the same time as we're reducing the negative impact, right? So people really think more about reducing the negative impact, but it is at the same time we should be thinking about increasing the positive impact, right? So how can I create a product that is not only not harmful, but it's actually beneficial to nature, right? Are there maybe in my process, are there maybe some other wastes that are coming off that I can use to be beneficial to something else, right? Again, like the tree that's producing oxygen along the way, right? That would be an example here. Right now, the way that we design stuff is what's called design for a landfill, right? So if you think about this sofa here, right, it has, I don't know how many different types of material, right? There's some kind of foams to make the pillow and the cushions, and there's fabrics, and there's wood. There's some probably metal springs. I'm pretty sure there's like, stuff is being covered in plastics to keep moisture out, and so on and so on, like a whole bunch of stuff. So it's really difficult to recycle something like this because you'd have to pull it apart. You have to divide it into each of its parts, and then what are you going to do with like old fabric, right? So it's not easy to recycle, or these foams are impossible to recycle. Another thing that we can think about is a bag of chips, right? If we just think about the bag, not even the chips themselves. This is here kind of the different layers that go into creating a chips bag, right? Because of course, a bag of chips, we want to make sure that what's inside of the bag stays inside the bag, and what's outside the bag stays outside, right? We don't want to have any oxygen get into the chips, because then the chips are going to go stale, right? We don't want the crumbs of the chips to come out while we're transporting it, right? So they have to stay in. We also want to make the bag look nice so that people see it on the shelves and grab it to buy it, right? If it's just a white container, then might not be interesting. And there's many different things, right? So we create this packaging that has all these different layers, and of course it's impossible to disaggregate those layers afterwards, right? So with a bag like this, the only thing that we can really do if we don't want to put it in the landfill is incinerate it, burn it. So that's not usually the best thing to do. But we can think about these kind of things, right? If we think about these from the very beginning, well, maybe we can design our products in a way that actually we can recycle them, right? So here's a chair, an office chair, and it was specifically designed to be taken apart, right? So that you can take all these pieces and assemble them so that you could recycle them, right? So there's the metal parts, like kind of the stand at the bottom, and this all looks to be metal, right? So if it's just metal in the end, then you could, metal is easy to recycle. You break down the kind of the plastic parts of a chair into its different types of plastic, and like some plastics can be recycled, right? Again, if you take materials, you'll learn that there's basically two types of plastics, and one of the types can be recycled because it can be heated up and kind of go back into a form that you can reform them with, where other plastic doesn't really, it's not really recyclable, right? But we can do all that stuff to then create a new chair or whatever else. But again, it goes along with the original design. Doing it afterwards, like most chairs you buy now, is really difficult to pull them all apart. One thing where this becomes really interesting are batteries for electric cars. Right? So obviously that's everybody's talking about electric cars, but if you want to have a good electric car, you have to have a good battery. And we haven't recycled that many car batteries yet because we haven't really built car batteries for a very long time. But people are thinking about it already, right? Because I think we're trying to be a little proactive with it. And so how can we design these car batteries so that we can easily recycle them afterwards, right? So, especially some of the real ingredients that we're really interested in is the lithium, for instance. Like, how do we make sure that the lithium that we have in a battery, we can kind of extract at the end of the life and create new batteries out of it. And there's some really interesting work going on, because if you think about the battery that goes into a Tesla, for instance, that battery is designed in a way that it's almost impossible to take apart. Because obviously, like, while you're using it, you don't want to have it to come apart, right? So even these little cells here, right, that make a bigger cell, they're all basically encased in epoxy, so you can't take them apart, right? So you have one big chunk. So really all you can do is grind it up and hope that you can do something with the component pieces. But there's battery manufacturers in China that are really designing these batteries in a way that they're easy to take apart, right? So that at the end of their life, they can be easily recycled. And this like, batteries for cars and other vehicles is going to be a massive problem to deal with, because if we want to have electric cars, we'll have to have batteries. We'll have to have big batteries. So again, like, we can design stuff to make it nice and recyclable, right? So this is a phone, a house phone, at least not one that's tethered, but nonetheless, right? So there's a whole lot of electronics that goes into a phone, a whole lot of casing, and so if you design it in a way that it comes apart easily, then you can recycle it. If it's impossible to get apart, then it's difficult to recycle. The kind of the side benefit of having something that actually can be disassembled is that if something breaks, you can fix it, right? So if, I don't know, if the display here, for instance, if the display breaks down for some reason, right, you don't have to throw away the phone. If you can relatively easily disassemble it, you can just put a new display in there, right? And then you save a whole lot of waste, because all this stuff was just working fine. The only piece that was not working fine was that one little piece, right? So it'd be great to do. And we can think about how we design, how we create stuff, right? So if we think about, again, if we think about the gecko, right, with like it attaches and it can detach. It has a very strong attachment, strong enough that it doesn't fall down, but if it wants to, it can detach completely, right? So if we could do that with our products, that would be great. Right? If we think about the LED screens that at least most of us are looking at right now, right? Then the way that LED screen is built, right, is basically there's a whole bunch of very thin layers that are glued together, right? And then there's the liquid in between that gets turned on or off to kind of give you, the shapes and colors that you want to see. Now it's very difficult to recycle these, because these layers are all basically glued together. Well, what if we had something like the gecko foot, where we can say, like, we want to have it stuck together, but now we don't want to have it stuck together and it just falls apart? Right? Obviously, there would have to be something, right? We have to heat it to a certain temperature, or maybe we have to run an electricity through it, or I don't know, some environmental thing that then would make it disassemble. Because of course we don't want to disassemble while we're using it, right? Well, we can think about this with many different things, right? If we had adhesives and ways of connecting things that were easy to come apart, then we could recycle many things in a much easier way. And then I think this is my second to last slide, I think, right? But another thing that we can think about is using our waste to create energy, right? So we're always talking about all the amount of waste that we're creating. Well, why don't we use those to create energy? One way that we have been doing that for a fair amount of time is we can incinerate our trash and then basically get energy out of it, right? Like, instead of putting, it's kind of the same concept of a coal-fired power plant. You just kind of stick your garbage in and incinerate the garbage, and that creates heat. And you can run a power plant now that comes along with a whole bunch of problems of what you do with the exhaust that's coming off of them. And people are throwing away a lot less plastic than they used to because of recycling, so stuff is not burning as well. But another way that we can do it is we can take animal waste, right? So especially when we think about big cattle farms and big pig farms, right? They create a lot of waste, and we can take that waste and combine it with some microorganisms, and they break it down and create. Anybody knows what this little molecule is? It's methane.
Methane.
Right, so we can create basically an artificial methane that we can then use to heat up the place where the cows are, or like create electricity to run the machinery that's milking the cows, or whatever, right? So this is something that people are already doing. And this is one of the things where, like, you think about the conservative farmer who doesn't want to try new stuff. But a lot of farmers have found out that this is actually a cheap way for them to fulfill their electricity needs. So people are using this more and more. And so we can create these very, very complex webs of taking waste from one side and using them for something else. So this is an example of a brewery, right? So they create beer, soda, and tea, and they have all these all these inputs, right? So they have some amount of packaging. They need to clean stuff. Obviously, they need the ingredients for beer, right? Yeast, grains, hops, and water. And then they need energy because you need to boil stuff. You need to keep stuff at certain temperatures to create a good beer, right? That creates these products, and then they get a whole bunch of waste, right? They get the spent grains, which is the grain where all the sugars have been taken out to create beer, the spent hops, right? So all the oils have been extracted, so that's no longer good. The yeast grows as you're doing this, right? Because it's a microorganism, so there's going to be extra yeast that you don't want to use anymore. There's heat that's coming off. There's a fair amount of CO2 coming off of when you're creating beer because when the yeast eats the sugars, it creates CO2 and alcohol. That's why your beer is naturally fizzy. And then of course there's a whole bunch of wastewater, right? So now traditionally they would have bought all this stuff and then paid more money to get rid of this. But like as you can see here, right, you can create all these other things that you could do, right? So you can do the spent grains, right? Grains, and then you can, be able to create mushrooms. From that you can create little worms, right? Those go to agriculture. That agriculture will feed back into the grains that you do. There's all these loops that you can create so that basically you're getting stuff out of your waste. And some of those are going to be internally, and some of them are going to be externally. And there's certainly places that a lot of people are thinking about the kind of the aquaculture of it, right? So a lot of the wastewaters that you would have a lot of nutrients in them, so you could feed them basically the fish tank and grow fish and sell fish, right? So I mean, you're a brewery, but every kind of income that you have is great. A lot of breweries are connected to restaurants, right? So you can say like we have fresh fish that we grow ourselves, and it's like super ecological because it's not being transported. Well, Costa Rica, that's obviously not so big an issue because the coast is an hour away. But like if you're in the middle of the US, right? So having fresh fish is not necessarily the usual thing. All right, I think that's all I had. And I think we're out of time too, so that's very convenient. Are there any questions? Oh, before we finish, I did want to mention something because it's come up a couple times, and that's about the journal. And that is the question about the hypothesis, because that's come up a couple times. And first of all, you don't have to, if you're not certain about what the hypothesis is or how that would work, there's always the version of not using an hypothesis, but just using 3 observations, which in my opinion is probably the easier thing to do. But if you want to have a hypothesis, then you have to have a bunch of observations that kind of lead you to the hypothesis, right? So for instance, if we think about bromeliads growing on a tree or something like that, right? Then you can make observations, right? Well, I see, you can do the form, for instance, say like, well, there are these little plants growing on other trees, and maybe you can make the observation, right, that there's usually not that many on a single tree, or maybe there are a bunch of on tree, many on one, just a couple on another. But like you have a whole bunch of observations, doesn't have to be the exact same observation that you're talking about, right? So we had people who kind of talked about a certain plant, and they say like, well, here's this part of the plant, this part of the plant, that part of the plant, all different kind of types of observations, but everything there leads me to this hypothesis, right? And this hypothesis should not be just a summary of all of your different of your observations, right? So if you have something, if I made the comment that you already said this in your observations, right, then that's why, right? So it has to be something that's coming out of them, but it's not just whatever you wrote for function, for instance. That's a common thing that gets doubled up. So I hope that clarifies. Marcela?
Yeah, I have a question with the journal. If I see like a pet of mine, like a dog or a cat or in the street or something, doing something like interesting, is that also an observation?
Sure.
Like instead of like a plant or a lizard, like just like a dog.
Yeah, well, look, I've seen many pets. I think I know most pets of you guys by the end of the semester. That's totally fine. As long as it's something that's a biological thing, right? So if you're talking about your pets and you're saying like, well, it's funny that this, like, I wonder how this pet evolved to have, this, poodle that has this strange fur, then it's like, well, it's not really a biological thing. It's, it's because you're cutting their fur, right? I mean, that's not really, that's kind of a different thing. So you kind of, when you're trying to make inferences about like how something evolved over time, then it really should be something that we're not directly impacting as humans, right? So I get things about like how certain like breeds of dog evolved over time. It's like, well, it's maybe not to their benefit, it's really probably to our benefit because we wanted to breed them in a certain way. Other questions? Then I think there's a couple people that want to chat with me about various details. So if you want to stay on and chat, that's fine. If you want to set up a time later to talk, that's fine too. Everybody else is we're done with class. Anybody who wants to leave is welcome to leave. Of course, the guys in the room should start vacating the room because the next professor is coming in. Yes, Danny.
So, oh. Well, I've heard that a lot of companies want to transition to like cradle to cradle design, but there's some people with proprietary technology.
Yeah.
So, some people